Welcome to the next video in the group theory series. In this video, we'll discuss permutations. But first, I want to give a little context. This course sometimes goes by the title Abstract Algebra, so you may be wondering, when do we start solving for x? Well, we won't be doing much of that. Abstract algebra does historically have its roots in solving polynomials, and eventually we will get around to that. But it won't be in the group theory series. We can only substantially start applying these lessons to solving polynomials when we study rings and fields. Even then, it only comes at the very end. So we probably won't see the subject of solving polynomials for a year after the recording of this video. So, although group theory historically arose from the search for roots of polynomials, it has since really become its own distinct subject with distinct interests. And in fact, permutations are among the core subjects of study in group theory. In a way, this example is not just another example, but is really the core example of a group. So pay close attention. Here you can see a preview of everything that we'll be discussing, so you can decide immediately if this video is what you're looking for. And on to the basic concept. So, permutations are all about rearrangements, so we need to start with something that is arranged. We can use the example of a word like ABC. You probably noticed that a word to a mathematician is not the same as a word to a normal person. To a mathematician, a word is just any sequence of symbols. Now, sequences are always distinguished by their ordering. So the word BCA is a different word than ABC, but they are permutations of each other. We say that one sequence is a permutation of another sequence if they share the same elements in the same quantity. This is a somewhat informal definition, which we'll make rigorous soon. To the left, you can see all of the permutations of ABC. It's here. Note that I've generated them with a system, which helps me to see that I've found them all. First, I generate all permutations that start with A. To do this, I first find all permutations which start with AB. Since the only one like that is ABC, this gets me 1. Next, I find all permutations which start with AC. The only one like this is ACB, so that gets me 2. 3 and 4 are likewise the result of finding all permutations which start with B, though through the same algorithm. Then 5 and 6 are those that start with C. The more mathematically formal way to view what a permutation is to see it as a function, sigma, with domain ABC and range ABC in this example. For instance, the permutation CBA is identified with the function a table with top row ABC and bottom row CBA, which tells us that A goes to C, B goes to B, and C goes to A. Notice that a permutation of a set X, like the set ABC, is not just any function. It must have certain properties. For one thing, it must be a function sigma from X to X. For another thing, there cannot be any repeat elements. So for instance, we would not call AAC a permutation of ABC because the former repeats A more than the latter. In the language of functions, this is the requirement that the function be injective. A function is injective if no two arguments map to the same value. Therefore, the function given in this table is not injective because two arguments go to the same value, namely these two, a and b, both map to the same value, a. We also require that no element of X is omitted. So AC is not a permutation of ABC because the former omits B. In the language of functions, this is the requirement that the function be surjective. Surjective means that every element Y in the range of sigma, there is some X in the domain such that sigma of X is Y. So for instance, the table with top row ABC and bottom row AAC is not surjective because B is in the range, but there is no X in the domain for which sigma of X is B. Now, one might reasonably ask, do we really need both conditions, injectivity and surjectivity? If a function is injective, isn't it automatically surjective? If the set X is finite and sigma goes from X to X, then it turns out that the answer is yes. An injective function is automatically surjective and vice versa. A surjective function is injective. However, we will sometimes consider permutations of infinite sets, and in this setting, it is possible to have a function which is injective but not surjective, and vice versa. For example, we write 1, 2, 3, 4, and so on. Down here, we write 1, 2, 3, 4, and so on. And we map 1 to 2, and 2 to 3, and 3 to 4, and so on. That is an example of something that is injective but not surjective. If we, on the other hand, built the function, which goes from 1 to 1, 2 to 1, 3 to 2, 4 to 3, and so on, that would be an example of something that is surjective but not injective. Therefore, we define a permutation on a set X to be any function sigma from X to X, which is bijective, which means injective and surjective. You can see to the left a table showing the function corresponding to every permutation of ABC. That's here. We define the set of all permutations on X to be this S sub X, which by definition is the set of all sigma such that sigma is a permutation on X. Now, although we fundamentally understand permutations as functions, there is yet another presentation of permutations which will be extremely important for us. This is the cycle view. Let's take, for example, the permutation given in table form of top row A, B, C, D, E, bottom row B, A, D, E, C. To find its cycle presentation, pick an arbitrary element, why not A? Now we chase it. In the table, we see that A maps to B, so we write down B. That's this much so far in the cycle representation. Next, we chase B. B maps to A, so it wraps back around to the start of the cycle, so we close it off with a paren. So that's that, right? So by now we've explained this part of the cycle representation. But because we haven't encountered every element in the set that we are permuting, we arbitrarily pick a remaining element, why not C? So we chase it, writing down C. We chase C to D, D to E, and then E back to C. So after E, we write down a close paren, and now we're done. So far, we only have a set of permutations. In order to make this into a group of permutations, we have to have some operation, some way of combining permutations. Since they are functions, a natural way to combine functions is to compose them. So that is to say, for all sigma tau in the set of permutations on X, the product sigma tau is equal to the composition sigma composed tau. That is defined by sigma composed tau on any element X is defined to be sigma of tau of X for all X and X. For example, take the permutation sending A to B, B to C, C to A, and the permutation sending A to C, B to A, C to B. This can be computed by first finding the image of A, which I'm going to use some non-standard notation to write that, but it is A being fed into the rightmost table. Recall that, right, you evaluate the right-hand thing first in a composition. So we evaluate A in this rightmost permutation. It sends A to C. Then we pass that C along to the next permutation, and C sends, that permutation sends C to A. So at the end, we see that A goes to A. Now we do it for B. We pass B into the first permutation, and it sends B to A. So now we're going to send A to the next permutation, and that sends A to B. So ultimately, we saw that this sent B to B. Finally, we pass in C. The first table sends C to, sorry, this should be a B, sends C to B, and then this table sends B to C, so at the end, the result is C. So what the above demonstrates is that this product of tables is equal to the permutation which sends A to A, B to B, and C to C. Now, it's not enough just to have a set and operation. They must satisfy the conditions for being a group. That is closure, associativity, identity, and inverses. To demonstrate closure, we must show that the composition of permutations on X is a permutation on X. That is to say, for any sigma tau, which are permutations on X, their composition is also a permutation on X. Let sigma and tau be any two permutations on X. We first need to show that their composition goes from X to X, and then that the composition is a bijection. Both of the facts are more appropriate to prove in the setting of a course on set theory, and therefore I skipped this proof. However, if anybody wants me to fill in this proof, leave a comment and I may get around to it. In fact, I will not prove any of the other properties either. Again, I regard them all as properly within the purview of set theory, and therefore relegate all such proofs to it. Still, let's at least describe in some detail which theorems we are borrowing from set theory. For associativity, we use the fact that function composition is always associative. This is true not just for permutations, but in fact for all function composition. For identity, we need to find some permutation which leaves the others alone when combined. That is to say, we need to find some iota in S sub x such that for all sigma in S sub x, iota composed sigma is sigma composed iota is just sigma. That's what an identity element is, right? It is easy to demonstrate that the identity function iota of x equal to x. That's a definition, right? So if we define iota to be this function for all x and x, if it is, it's easy to show that that is such a function. One must also confirm that iota is in S sub x, which is to say we must show that it has the appropriate domain and range, and iota is a bijection. That iota has domain x and range x is just by definition, so that's really nothing to prove at all. That iota is a bijection is a trivial proof, which the viewer is encouraged to fill in. For inverses, we need to show that every permutation on X has an inverse permutation on X. That is to say, we need that for every sigma in the permutations, there exists a permutation tau, such that sigma tau is tau sigma is iota. That's the whole concept of an inverse. They combine to the identity. One idea that should immediately spring to mind, the inverse function. We will help ourselves to the set theory fact that every bijection f from A to B has an inverse f inverse from B back to A, which is also a bijection. In our case, this guarantees that for all sigma, there exists a tau such that tau is sigma inverse, and therefore, since sigma went from x to x, then tau goes in reverse, but that's just, again, x to x. And tau is a bijection. Therefore, tau is a permutation on X. So we have it, that S sub X equipped with composition is a group. We call S sub X equipped with composition the group of permutations on X or the symmetric group on X. Often we don't actually care about the elements of X, but just care about the permutations. Therefore, we just use a canonical set to serve as our X. The only thing that importantly distinguishes each X is its size. So for a cardinality of n in the natural numbers at least 1, we take the canonical set to be the set from 1 to n. Also, for a countable cardinality, we say that n is infinity and take the canonical set to be the set of all positive natural numbers. Then, instead of writing S with the subscript this whole set, in either case, instead we just write S sub n, where n is any one of these numbers, either a positive natural number or infinity.